So why are we here? What do we mean by high performance in cold climates? Here's a fun picture to look at. Won't say whose house this was unless that person wants to comment. But just wondering anything you observe here. You're welcome to add in anything you note from the chat box. But if anyone does want to unmute and just mention anything you see that you might think is not high performance, please feel free to unmute and say something. Anyone want to be brave and comment on what you see?
It looks like there's condensation on the roof.
Yeah, so I think what we're actually seeing here, this was a chilly morning. I don't remember what time of year, if it was like spring or fall. I think it might have been kind of early fall. So yeah, we were seeing frost here and less frost here. And then here, you're basically seeing no frost at all. It's just completely melted. And in the interest of everything we want to get through, rather than dwelling too much on this, well, and then another thing you'll see is the gutter is kind of, has been misshapen here. So if you're on the inside of the house, what you would see is that there's a drop ceiling in this half of the roof. So this is all drop ceiling. This is an attic space with insulation at the ceiling level. This attic is supposed to be cold. Vented attic, this attic in theory should actually be cold. This is a cathedral roof that I believe is probably spray foam, but then we see all these melted areas. So what's actually happening here? In a high performance roof, everything would have frost. This roof would be cold. It would not be letting heat from inside the home out. And in this case, there's clearly heat getting into this attic space that's supposed to be well insulated. And you know, in keeping the frost off, that you can see where there's foam that looks to be doing an okay job. But what's happening in all these melted areas, I'm guessing some of you have an idea, and your instinct is probably right that these are can lights on the other side, supposed airtight can lights that are insulated all around. So this is one of many things you'll see when you look around at roofs in cold climates that is indicative of again excess heat loss and not high performance. So these are the kinds of problems and challenges we want to solve through thoughtful building design and implementation of good construction details. And I don't know for sure if this stems from it. This could just sort of be random, but I think what's happening is, you know, there's a lot more snow sliding off of this part of the roof and is causing more gutter damage. My kids love icicles, but again, not a good sign of a high performance building. Lots of heat loss through a lot of roofs when you start looking around here. We don't want to see icicles. We don't want to see ice damming that you know, damages roofs, tears off gutters. Not a good thing. And supposed high performance dual pane windows are really not so high performance when it's 10 below zero outside. This was a probably 10-year-old window in a home in Bozeman. So these are some of the problems that we can solve with high performance building. Careful attention to a well-designed building envelope. And you know, great, Montana's second, Wyoming's third. Unfortunately, that means second and third to last in terms of amount of energy use per capita. So we use about, you know, in our states, we're using more than double the energy of the typical California resident. And you know, there's clearly a correlation to higher energy use the further north you go and more heating dominated climates. But yet look at Minnesota, look at New York, look at Vermont. These are doing something, you know, Minnesota's doing something that North Dakota is not. And we can do better. So these are all the reasons why we want to focus on high performance, especially in our extremely cold climates. You know, another reason we care about this a lot in our work at Beyond Efficiency is about energy equity. A lot of our work is in affordable housing. And a large percentage of Americans have significant energy security issues. 31% in the year that this was done in 2015 reported some sort of household energy insecurity. And about 1 out of 5 households is foregoing food and medicine to pay an energy bill. So it is in everyone's best interest, especially lower income communities, to incorporate practices in our buildings that reduce energy bills. So here's the approach we like to take with any of our projects. This logic really applies to anything you're looking at, whether it's conserving water, conserving materials, in this case, conserving energy. You can take this logic anywhere. You want to start by trying to eliminate the problem from the outset. In this case, if we're talking about energy, what do we do to minimize energy demand? We use things like triple pane windows. We focus on a very airtight building envelope. We use much thicker, more highly insulated walls than code would otherwise allow. To mitigate cooling issues and the need for mechanical cooling, we want to properly integrate shade trees, be very thoughtful about roof overhangs or awnings, incorporate a radiant barrier if you're in a real cooling dominated area, which is not so much, we don't have to worry about as much in Idaho, Wyoming, and Montana. And once we've done a good job of, again, just of minimizing demand through just plain old good design, then with the energy that we do need to use to provide heating or cooling or hot water, now we want to think, how can we put that energy to its highest and best use? One example, very relevant here, and we'll talk a lot about it today, is using heat pump technology, not electric resistance. We want to optimally route our ductwork and our piping, make sure ducts are tight, energy efficient lighting and appliances. Then we land at having the pretty low amount of energy use, and that's where we can then come in and incorporate renewable energy. If you skip these 2 steps and someone wants to be zero energy, but they likely need more roof space than they have to get to, say, zero energy in a cold mountain region like this. And especially with limited subsidies in our area, you don't want to put more solar panels on than you need. One of my favorite pop questions is, what's the cheapest kilowatt hour? It's the one you didn't need to buy. So that's really what we're talking about here. And this came from Lower Valley Energy's website, which is what serves our community here in Jackson. And this basically looks at different fuel types and says, how much does it cost for a certain amount of heating that you're getting? Electric resistance, a little over $16 per, what does MM stand for? Mega million or whatever. If anyone knows MMBTU, you can speak up. Essentially though, we're talking about a certain amount of heating. Natural gas, you can cut your cost by about 1/3. So a lot of people say, okay, great, I want to go to natural gas. So what is not shown on this chart that really should be on the chart? Yeah, it's using heat pump technology. So if we use heat pump technology, even in our cold climate, where heat pumps, when you get down to pretty cold temperatures, are less efficient and potentially will get to the point where they don't even work, and you then have to do electric resistance, still on the balance, being very conservative. If electric resistance is costing $16 for a certain quantity of energy, you can be spending half, if not even 2/3 less, depending on other aspects of the project, on heat pump technology. So we would really love to see a lot more effort being put on heat pumps in this climate. So some best practices on envelope. But first off, when we talk about heating demand, what does that really mean? So if you just look around the room and the space that you're in, you are right now, there's conductive heat loss through your windows. It's colder. Actually, what's the temperature right now? That might not be the case. Let's just say it's a fall day. It's 40 degrees outside, and it's 70 degrees inside. We're losing conductive heat through windows and through walls, through your floor, through your roof. Accidental air infiltration or exfiltration from not having a very airtight building envelope. And then finally, just to ensure good air quality, we do need a certain amount of air exchange, ventilation. But bringing in 40-degree outside air, needing to heat it up to 70 degrees, of course, has an energy impact. So these are the typical ways we're losing heat. But then on the flip side, we're also, heat is being added to the space by solar radiation through windows if it's not nighttime. Internal gains, hot water cooking, just breathing. And so it's this, and what do we do to make this balance? That is what we call heating demand. So that is the amount of heating, you would talk about it usually in BTUs per hour, or an absolute amount of energy that might be needed over a day or over a year, that will be provided through a furnace, natural gas furnace or propane furnace, heat pump with an indoor fan coil, something like a hydronic fan coil, again, a number of different ways to provide that heating. So what we're talking about in best practices is let's minimize these losses in order to minimize the heating demand, which then allows us to minimize the equipment, make that as small as feasible to still maintain comfort, keep people alive. So how do we go about this? Again, number one, minimize heat losses. To know where to focus energies, we need to first understand what, if you picture a pie chart that's showing the breakout of heat losses between these things we just looked at here, what are the biggest offenders in the small scale commercial, the typical residential project? Always, the big three are walls, windows, and air infiltration. If we already have an R60 roof, we're just not going to get as much benefit from going up to R80 as we are going from an R24 wall to an R30 wall. Walls, windows, and air infiltration really are always the places to focus efforts. This was a project we worked on in Telluride 5 or so years ago. Nice, modest, I think about 1,600 square foot home, designed by Architecture Architects. This is the finished that was the finished product. And what you are looking at here under construction is the wall assembly. So this project wasn't going for a super aggressive standard like Passive House. I'm actually not going to talk a whole lot about Passive House today. I think in some of the following webinars that will be discussed more. But essentially, the Passive House standard is built on these best practices I just talked about, which is, hey, let's first just design good building envelopes to minimize heating and cooling demand. That's where we should start. So this project took a kind of a pragmatic approach, definitely went above code, but didn't do anything that some people might call extreme. So this green, the dark green you're seeing here is a sheathing panel called Zip System, which I'm sure a lot of you are familiar with and have worked with. This is just it's an OSB sheathing panel that essentially has the weather resistant barrier, or WRB, pre-adhered to it. And it's inherently airtight. Once you install it, you need to, you treat the seams with a Zip System tape, and it ends up being a really robust, just great end result that also gives you really good airtightness. There are zip panels that have insulation on the inboard side. That can be a challenge with seismic calculations and things. But the Grove project, Grove Phase 3 here in Jackson, did a zip panel with, I think, 1 inch of insulation. So it can be a nice way of providing that continuous exterior insulation in the wall assembly, but simplify it a great deal. Otherwise, really the best practice approach, and there absolutely is cost and complexity involved in this, but we very strongly encourage this on our projects, is to do continuous rigid insulation outboard of that sheathing, whether you're doing Zip System sheathing in this case, or you're doing a conventional sheathing panel with a different WRB approach. In this case, it's 2 inches of mineral wool, and then these are furring strips installed on top that then the cladding is attached to. And here is a blow up of this detail at the window head. So in this case, 2x6 framing with dense pack cellulose insulation, the sheathing with the drainage plane, and then 2 inches of mineral outboard. A lot of people have questions about where to put the drainage plane, feeling like that always has to go outboard of the insulation. A good way to think about this is the insulation doesn't care if it gets wet. The WRB, the highest and best purpose of the WRB is to protect the weakest point in this wood framed assembly, which is the sheathing. So my best practice, my favorite approach is this sort of assembly, where you have cavity insulation, we have the sheathing, we have the WRB directly on top of the sheathing, which again is the weakest point. This also is functioning as the air barrier, so the insulation outboard of it is giving that weather resistant barrier that much more protection. And this continuous layer is very important to just to add R value to the wall without going to 2x8 or 2x10 framing, and also to have all of that framing in the wall, which on average nationwide is about 25% of the wall. Meaning if we were to add up all the double top plates and sill plates and king studs around windows and everything else, headers, extra blocking for seismic collectors, about 25% of that wall is wood. Wood obviously is not insulation. It's not bad. It's much better than steel, but it's still losing heat about 4 times faster than insulation. So if you have continuous insulation outboard, it mitigates the thermal bridging and melting of ice on roofs and things like ice dams that you'll see in our cold climate. So yeah, this is definitely a concept we highly encourage. There's a lot of concern in a detail like this of, well, how do you attach the mineral wool? How do you attach these fraying strips? How can you be sure you're hitting the studs when you go through? People are concerned about mineral wool compressing and the siding deflecting. In reality, the loads, the service loads, even from fairly heavy cladding, are very low in relation to kind of the whole system. And rather than getting more into that, which could be a 2-hour talk in itself, you'll see this link again in the slides that we'll follow up with. But RDH Building Science is a great consulting firm with offices all over the country, and they have a really good presentation that gets into this. And I just shared this one attachment product that can also facilitate these sorts of installations that have these identically pitched threads, and it essentially, these will allow you to let's see, I'm losing my notes here. Anyway, this will allow you to attach these products without overly compressing the insulation and the issues that might come with that. So again, all of these challenges can be solved. It's just having the goal in mind and deciding you're going to do it. So a question I always get is, why not just foam it? Well, here's just one example. You can see where these roof rafters are losing heat and melting the frost on this roof. There are other issues and concerns about foam, and again, we're going to focus more on systems today and not talk about things like overall carbon footprint, embodied energy of products. But when possible, we encourage building assemblies that are designed to not need foam. And there are some cases where you just really need it. It's just the best product. In that case, fine, great. But we do otherwise encourage foam-free assemblies. So what are good window selections in our climate? One of the things I have here is strategic solar heat gain. SHEC stands for solar heat gain. So something I've seen happen a fair amount in Jackson is, people will say, hey, we want to build this really thermally efficient building, and they'll go to their window rep and they'll say, okay, we want your lowest U value window you can give us. And so that's what they'll get. And the problem with that is the lowest U value, which again is highest R value, is by default, that comes at the expense of solar heat gain. So you might get a 2% better U value, which is great, all things being equal, but it could have 30% less solar gain. And in our climate, we get so much benefit from solar gain that in most cases, that really should be the rule if you are going to look into it more. So we really do need to think about what's that balance between wanting lowest U value, but also wanting high solar gain. You need to think about the total energy balance of the window package around a building, and be thoughtful about that. You know, and in some cases, all the gorgeous views are to the west. There's significant thermal comfort concerns and just cooling load concerns. And that's a situation where it definitely might make, you know, it certainly could make sense to do a low solar heat gain specification on that window. But as a rule here, you know, just be careful of asking for the lowest U value product, because on the net annual basis, when we look at total energy balance on the whole building scenario, you could significantly increase your heating load. Now, best practices for windows: fixed are best in terms of just upfront costs and also being very airtight. Casements and awnings, just by nature of having that positive closure when you lock, are generally pretty airtight. Lift and slide is a newer technology you'll see for sliding doors that can actually be very, very airtight. Otherwise, you really want to minimize sliders and just never do hung windows. Again, you know, there are always exceptions. People have a certain look or they need to replace something in kind. Just being aware of these best practices, I think, is always helpful, regardless of what decisions do make sense for a project. This is a map showing the amount of solar insolation that we get in our country. And here's where, you know, where everyone except in Montana is, Western Mountain region. There's a lot of sun to be had. It can be ours for free if we're thoughtful about integrating it in an appropriate way. This is something used in a passive house tool called the Passive House Planning Package. And the real thing I want to point out here, if you just look at the yellow line, this is showing in Jackson on average how much solar radiation would fall on a vertical south-facing surface. And 1 and 2, January, February, March, you can see, you know, we have a lot of need for heating in those months, and we're getting a lot of solar gain. So again, thoughtfully and appropriately designed south glazing that's also shaded so that it doesn't cause major overheating issues in this time of year can be hugely helpful. You know, I used to joke that the Grand was put in the wrong place when Jackson Hole was formed, because that's where the views are. So again, there are always constraints and realities of a project, but the point is just to be aware of these and don't skimp on south windows. Even though we have 20 below, 30 below days, on the net annual basis, south glazing, assuming just even a basic dual pane window, will be a net benefit to a project in Jackson and our other mountain climates. So air tightness was another of those big three. Very important in our climate to focus on high air tightness in the building envelope. The adage is build tight, ventilate right. If we have a very airtight building envelope, if you then have control over how much mechanical ventilation you want to provide, and you're not just sort of hoping that air leaks from around windows and indoors are enough to provide the ventilation needed. So to provide air tightness, again, I really do like designating the structural sheathing as the primary airtight layer. It's adjacent to the insulation. You can protect it with that continuous exterior insulation. It's just a really good strategy for a 100-year wall. And then rather than floppy stuff that will, you know, it can be pulled apart when the wind gets in there, cause rips, won't name any products, always very strongly encourage a self-adhered product. So we already talked about zip system sheathing. There are other self-adhered membranes. One we like a lot is this one by Vapor Shield. There are roller spray-on products. They're a bit more labor intensive. Number of different ways to go, but by far the best approach for long-term durability that also gives you that air tightness. I'm going to highlight a little bit about the Bridge Your View redevelopment project. That was a rendering you saw on the main on the intro slide, and this is a project we're working on up in Bozeman. Really lovely small neighborhood development with 62 units. with, again, modest home sizes and a variety of unit types. And this project went in and still has very high aspirations, is using passive house targets to guide some of the decisions around building envelope, and is also going for the Department of Energy Zero Energy Ready program and LEED for neighborhood development. And there's been, yeah, really great team collaboration between ownership and architects, structural engineer, contractor, to assess a wide variety of approaches for things like attic versus cathedral roof, you know, panelized walls, stick framed, different materials. And where this has landed is that these will be vented attics, which is just significantly less expensive to get to a high level of performance, rather than doing, say, 6 inches of cork outboard of the sheathing, which otherwise could have been a great solution, but very expensive. And one challenge with this is that the air barrier will be, again, at the ceiling plane, and we don't have that nice rigid sheathing to designate as the ceiling plane. So this will be one of the challenges in terms of the construction phase, to make sure that that is installed in a very airtight way. But this is what we landed on for the roof assembly. This project is just now starting CDs, and this was just a markup we had done on a DD detail. But this will be, again, similar to that Telluride project I shared, 2x6 framing with dense packed cellulose. In this case, again, there was a lot of back and forth about different materials to use outboard, 4 inches of cork, mineral wool. Again, a goal had been foam free, but it's just really difficult to justify the cost on a project like this that has such high aspirations and otherwise has, you know, every project has its budget challenges. So this is a nail-based 3.5-inch EPS, and it's gonna, yeah, end up being a really good end result with a fraction of the heating related energy use that otherwise would be a code level building would have seen. And Lakin, have any questions or comments come up that we should catch up on before we jump into HVAC?
Yeah, we have a couple. So the first is Kate Ryan asked, at some point, can you address the tightness of an energy efficient house and the risk of trapping radon or other risks of having such a tight house? And Phil, our friend Phil Cameron.
Let's actually tackle that one real quick. So yeah, so the question is, it's concern about having a home that's too tight or a building that's too tight. So every building needs ample ventilation, that's a given. The question is, are you hoping you're going to get that ventilation through random air leakage, or are you going to deliberately provide it with mechanical systems? And the problem with hoping you're going to get enough ventilation through just leaks is that you have no control over it. Depending on the temperature differential, how hard the wind is blowing, just the design of a building, you could get way more air infiltration than you need on a certain day, or get a fraction of what you need. So you have no control. So that's why, again, the best practice is build tight, ventilate right. And let's see. So I don't know if did I completely answer that question. So another good thing about once you have a tight enough building, if you're providing your ventilation with a mechanical system, you then have the opportunity to incorporate heat recovery, which is something we'll talk about more. But that can dramatically reduce the energy aspect of what it takes to ventilate your home or your commercial space, your school, whatever it might be. You know, what we've found in our projects is once we've landed on a good building envelope, whether it's passive house level or it's pretty good house or whatever kind of reference you might want to use, we generally find that ventilation becomes the dominant contributor to heating related energy use. And if you then reduce that aspect by 80% because you have heat recovery, you know, you're suddenly dropping the heating component of your building's energy on an order of, you know, you're reducing it by 70 to 80% when you look at a really good building envelope combined with heat recovery ventilation. Now, when it comes to something like radon, that's really, again, a function of just doing a great job under the slab and properly designing your radon system. I would say then to ensure that your radon system really is depressurizing that under slab or crawl space area, and keeping the radon out, having a balanced ventilation system that isn't actually competing with that radon system is going to make it that much more effective. So if I didn't answer that, please do chat again, and we can get into that more. And you said Phil had one also?
Yeah, Phil had kind of a piggyback question to that. Just asking for you to discuss more how you can efficiently bring in makeup air for combustion devices like wood stoves to overcome tight or construction like retrofits.
So we are going to talk about makeup air, so we'll get to that in HVAC. Thanks for the
Okay.
segue.
And then I do have one window question from Michael Best. Do you ever mix the specs on the windows based on wall elevation and other considerations?
Yeah, so the question is sort of tuning windows by facade. I think there are definitely situations where that makes sense. You do run the risk of window orders getting messed up, or a window getting installed on the wrong facade if it's otherwise the same rough opening size. But that's a problem that can be solved. And I think tuning windows actually can be very effective. I would say in our climate, the easiest thing generally is just do high solar gain everywhere, except for south exposures where maybe it really isn't possible to properly shade them in the summer, or on those just larger west expanses where the added heat gain really could be a problem. So yeah, tuning windows is a very real thing. We've done it on a number of our projects. You just need to be a little cautious. Okay, should we get into mechanical? So something that in our consulting practice we've been migrating more and more towards is all electric buildings. A lot of our work is in California, and the state of California has been aggressively pushing all electric to get off renewables and ultimately achieve carbon neutrality goals as soon as possible. It's a very different, and then here in Jackson, it's interesting because a lot of existing buildings are all electric because electricity is so cheap, and installing electric resistance heating or water heating, space heating or water heating is so inexpensive that a lot of buildings are all electric. Anyway, won't get it too much into why we like all our electric. I mean, aside from the being able to plug into a cleaner and cleaner electricity grid, it's just you're not running gas lines. You don't have risks of safety issues from gas. Forget how many people died in a gas line explosion in San Bruno in California less than 10 years ago, and that's just the first one that comes to mind. So all electric we really see as the future, and I think people have been hesitant in cold climates because there's this conception, arguably misconception, that heat pump technology just can't work in cold climates. In fact, it can work. You just have to know what the limitations are of this equipment and know how to integrate backup systems when a piece of equipment can't operate at, say, -10, and know that on the balance, if a piece of heat pump equipment is still operating in that in heat pump mode, that on the net annual balance, you're still significantly improving the energy efficiency and reducing energy use for a property. So here's a concept that is an interesting approach, is what I would call, again, efficient and affordable all electric heating, but that it's more expensive than doing all electric resistance, but less expensive than doing only a heat pump or a primarily heat pump based system in a building. So this presumes that heat recovery ventilation is a given, because that will serve to reduce that heating demand that needs to be made up for with your space heating system. And then the thought is, let's use a very efficient system for the main space, the main living area that tends to have the largest area of heat loss because you usually have the largest windows and living area, dining area. That's where people are hanging out most of the time on a chilly evening before bed. So you focus the more expensive system on that main space to get the best benefit of that high efficiency system. And then do it super cheap, the rest of it. Bedrooms and bathrooms, electric resistance. If you're already designing a high performance building, and a lot of people like me, certainly not everyone, but likes a pretty chilly bedroom to sleep in, you know, I think you can justify this kind of hybrid system. And this is exactly the system proposed for that Bridge of View project that I already have talked a little bit about. You know, we're still really in pricing, but from what we can tell at this point, it would be a savings of at least $4,000 a unit, a dwelling unit, with doing this sort of hybrid approach rather than doing the mini split heat pump, ductless fan coils in every bedroom. And, you know, $250,000 in project savings. So we're still not sure exactly where this will land, but this is one of the potential directions for it. So, you know, things don't have to be all or nothing. You can get creative and think about where the biggest air, you know, room spaces are to focus energy and potentially prioritize that high efficiency system there. So what is a mini split heat pump? We haven't even really talked about this yet, but you know, the heat pump technology for a minute. A heat pump is actually extracting heat from ambient air rather than just directly creating heat through electric resistance. So the warmer the temperature is of that ambient air, the more heat there is in the air to extract and pump into air that you're going to put inside or pump into water, whether it's for space heating or water heating. But this is really the concept. This is just one of the many systems available. This is Fujitsu. We tend to actually use Mitsubishi more, but you have an outdoor unit that then feeds various indoor units. This could go in, you know, a living room. Maybe you have a separate one in each bedroom. You can have ducted. You can actually have recessed indoor ducted fan coils that would then have short ducts into spaces if you don't want this unit hanging. And then there are also these ceiling units. This is pretty typical of these mini split systems. So that's the concept of heat pumps. And then, you know, another way to do a higher efficiency space heating approach in a cold climate is air to water heat pump. And yeah, Kara, anytime, please jump in and offer thoughts and other comments here. But this is a project we're consulting on in Wilson. There's a main house and guest house, and the guest house has been completed first. And this is using a Solstice heat pump, air water heat pump that then heats water in a tank and then can feed in-floor heating or other, you know, terminal units. And in this case, in this particular project, this is just a schematic actually from Solstice. This is not from the project. In this project, it's all in-floor heating. I think I'm remembering right, Kara?
Floor on this one.
I think we missed your first sentence.
It is in floor on the guest house, yes.
Yeah, I might let you, if you could keep yourself unmuted here. So, and then Kara, looked for you to speak with just one. There are all kinds of considerations with proper heat pump design, whether you're in a mild climate or cold climate. But in terms of some of the highlights of cold climates, here are some of these. And yeah, Kara, please jump in and say anything you want to say on these.
I think this slide pretty much covers it. This applies for air-to-air and air-to-water heat pumps, and we haven't talked about it yet, but the stand-in heat pump water heater, the outdoor unit for that, they all kind of they have the same guidelines. Some of them, Sandon has more specific ones. So just make sure if you are specifying one of them that you're checking with the manufacturer that you're using to make sure that you are covering all of their cold climate guidelines.
And
Yeah.
Katie, we did have a question about the mini split heat pumps and whether they're a good solution for multifamily buildings as opposed to our single family example.
Yeah, absolutely. I think mini splits can be a solution really for any building type, whether it's single family, multifamily, commercial. And I guess I would say the challenge we can have with them in our designs, which actually is less of an issue here just because it's colder, is that the indoor units they have their rated output, and if your load in a space is just that much lower, but yet you can only go so low with a certain terminal unit, you can just get into cycling of the unit, which is just not good. We always want ideally a unit to be properly sized for the, it's properly sized for the load. So we have less of an issue with that here. But if you do have a multifamily unit, even in our cold climate, we likely, these units would be oversized if you have like one indoor unit on say 10 by 10 bedroom that's on the third floor of a building that only has one exterior wall and one window for heat loss. There's another dwelling unit above, another dwelling unit below, living space outside of it. The load in that space is going to be, quite low. So that's where these ducted units can be a really good choice. You can have, again, just one unit that you would duct to these rooms. But yeah, absolutely, really, really good way to do it. With multifamily, another aspect that can be a challenge is that ideally there would be one unit for each dwelling unit, and if you have a large multifamily building, that's a lot of outdoor units. Where do you put those? So just there are always things to think about.
And then one more question on heat pump, water pumps. Have we used the Sandon for in-floor heating systems such as those offered by Radiant Tech?
We have, and we can talk about that when we get into we actually have some slides on the Sandon. Tends to not be a great option here just because of our higher heating loads, but yeah, we can definitely be sure to answer that question. And yeah, just to highlight one thing here, understand the load curves. I've seen, I was involved in a project once where this was not local. This was a kind of Northern Idaho project where the mechanical design build contractor had a heat pump specified and thought that it was going to meet the loads of the building. And then I realized in looking at their kind of specs that they had just sort of taken the rated output, and I think it was listed for 32 degrees, and yet the design temperature in this region was 5 degrees. And at that temperature, the output of this unit was, it was only going to be about half the load. I mean, it's sort of mechanical design 101, but it's really easy for those sort of basic things not to happen. So, just, yeah, understanding the load curves is important. And then below a certain temperature, the cold climate versions generally will go down to about -13. Below that, they just basically stop working, Kara? Is that what happens?
Yeah, it depends on the equipment, on what they tell you. Each manufacturer will tell you something a little bit different, but I would not plan on having any heating past, depending on Mitsubishi Minisplits, I think say -13, they're working on going lower. Air to water heat pumps is usually around -5 to -8.
Can I just jump in and explain from kind of a layperson's terms about heat pump technology and why it's so great?
Absolutely.
And please correct me if I'm wrong, because I'm not the mechanical engineer here, but my understanding is that it takes the heat from a source, water or air, and that heat might not seem like heat to us because it might be colder than the temperature that we're trying to get to. But with the use of a refrigerant, it takes the heat from that source, whatever it can extract, and then applies it to the air or water that will then be distributed into the space. So the efficiency of them works really well when the differential between the source and the ideal air temperature is very low. And when the temperature gets very cold outside, the ideal temp stays here, but the efficiency really drops because it has to make up this huge gap.
I think, yeah, I think you said that perfectly. And we have a chart on some of the Sandon, the Sandon coefficient of performance factor, COP, that will that will highlight how that drops. But I think you'll be surprised though, that while the efficiency drops, it's still, even at these really low temperatures, I mean, this technology has just evolved leaps and bounds the last 5 or 10 years even. It's still, twice as good as electric resistance. And even if you completely get locked out, you're only in electric resistance mode, you're talking that happens a couple weeks a year. So on the balance is still a really good way to go. And, on that note, yeah, Kara had me add this as a good point of if you are designing something and you realize that you are going to need backup heat because of the design temperatures and the system you're using, that it can make sense to size that heat pump for the cooling load in that case, and you just get what you get out of the heating components since you're going to have that backup anyway. So that can be something to keep in mind. So again, we talked about ventilation, build tight, ventilate right. I think using a heat recovery unit or energy recovery, essentially the same thing. It's just that the energy recovery is also helping to recycle moisture, is just such an important aspect in these cold climates. So essentially what these units will do is they will, rather than bringing in 30-degree outdoor air, exhausting 70-degree indoor air that has moisture, cooking smells, everything that you want to get out, and having to then heat that 30 up to 70 again. The heat recovery ventilator, will pass the airflows through heat transfer plates or technologies, depending on the system, but without actually mixing the air streams. It's just basic counterflow or cross flow physics. And it can recover, with a decent unit, 80% or 85% of that heat, meaning if let's say you had a 75% efficient heat recovery ventilator, you're bringing in 30-degree air, you want to get it up to 70. Instead of that dumping 30-degree air into the space, it'll dump it in at 65 if it was a 75% efficient unit, roughly speaking, easy math. So it's, helps with comfort and just hugely reduces that heating related load. So highly recommend that as a best practice. And then one other thing here, yeah, essential for cold climates. And, the little asterisk I have here, generally as a default, I feel ERVs are a good choice for our cold, dry mountain climates, because in the winter, when we have, if everything gets really dry, you want to keep that humidity in. But again, you always need to think about what's the situation. What is the particular space you're designing for? And if you're designing a multifamily building that's catered to families, and you've got a 800 square foot apartment with 4 people living in it, it's a lot of added humidity just from, again, people breathing, a lot of cooking potentially. So it might be bad to have an ERV in that space. So again, always just need to be aware of what the situation is. And on the cooling side, I think if things are generally speaking, we should be able to design structures in Jackson and other mountain regions to not need cooling. But cooling obviously can be a great thing and add a lot of comfort. But getting back to passive principles, ideally we're incorporating exterior shading for solar control, something like this. Interior treatments can be really helpful with mitigating the discomfort that might happen from the sun just beating through the west-facing glazing. ceiling fans can be amazing with comfort. We've kind of forgotten about a lot of this since we are, you know, people just sort of tend to do air conditioning now. It's like, oh, let's forget about just basic passive approaches, low-tech approaches, and just do air conditioning. Again, not to knock air conditioning totally. It's obviously a great feature, and we should embrace it when it makes sense. And, you know, one note on this aspect of thermal comfort, we tend to think of thermal comfort as just where you set the thermostat. It's just what the temperature is. Oh, I think I messed up on my animation here. Uh-oh, what happened? Oh, sorry, I somehow lost my images here. So I'll add these in to the slide so that you can see them when you review. But I had a couple of things highlighted here from this thermal comfort tool, and essentially what it's just showing is the benefit you can get from turning on a ceiling fan. You could be cooking in a space with work clothes on because you just come home from work after COVID, and the air temperature is 80 degrees. You can probably guess who'd all be uncomfortable. What this tool shows is as soon as you turn on a ceiling fan, most people will actually be comfortable. So sorry we missed those. It's actually a really great tool. And we're late on, getting close to the end here. So I think I'm gonna skip quickly through to our to the last discussion on hot water. But yeah, this was just another note to help people remember the power of the sun and the radiant gain, and to be sure that that's being kept in mind when we're designing mechanical systems and thinking about like, oh, do we just provide a bunch of cooling in a west-facing space and everything's good? Or is that really gonna ensure thermal comfort in a space? So hot water, now we're onto the sand end. This is a picture actually not from a cold climate project, but otherwise a project that uses sand.
Katie?
Yep.
Sorry to jump in, but it is, it's pretty much one. And I feel like we could totally go down a big rabbit hole with this. So maybe if people want to stay on and keep going, feel free to. But in case people do want to wrap up, I just wanted to mention one last thing, which I should have mentioned at the beginning, that Love Shack and EMU Building Systems were hosting, and TKG Construction were hosting a passive house builder training in Jackson this spring, which got paused by the pandemic. That training is still happening behind the scenes. It's gone online, as have all of our conferences and things lately that all of you are probably very familiar with. We had hoped to have this great community event at the end of that training with all of our partners in this space of high performance design in our climate, including Beyond Efficiency and TKG and Energy Conservation Works and who am I forgetting? NAPHN and EMU. So we took the opportunity to generate this series of webinars, and just wanted to thank you all for participating. And please reach out to us if you want to engage in any other way. AIA Idaho has reached out to us and would like for these webinars to provide CEU credits, so that is happening. And if you are part of an organization that would also like to gain CEU credits, reach out to us and we'll see if we can make that happen.
Okay.
And with that, I think, and feel free, I think that's kind of the ending note for the moment, unless you want to stay on and Katie will keep going. And I will mute myself again.
Thanks, Lindsay. Yep, so it is now 1 o'clock on the dot. And this was the last discussion, just talking about heat pump water heaters in general. And would welcome anyone to stay on. I had hoped we'd be able to do just sort of some general back and forth Q&A. We've, I think, covered a lot of that as we've gone here. But yeah, if anyone wants to stay on for another 5 or 10 minutes, happy to take on a few more questions. These are specs here on the stand-in. This is actually a CO2 refrigerant-based heat pump water heater that has the best efficiencies across the heat pump water heater market right now. And you can see that it does operate down to -20. And, you know, we just highly encourage heat pump water heaters and no longer electric resistance. We can make them work in this climate. You know, there are design considerations, but they can work. This is just showing their split systems with the outdoor unit and the indoor tank, like the stand-in, and then there are unitary systems with a heat pump connected, which potentially can be used indoors in our climate, as long as you're then providing a high efficiency heat source to that space. Since most of these units otherwise tend to really only operate in heat pump mode down to about 40 degrees, these unitary versions. And this is just a schematic of a stand-in design for the heat pump water heater that we won't get into here, but will be there in the slides if you want to check it out. And then Carol will be there to explain what all this means. So again, yeah, happy to stick around another 5 or 10 minutes if anyone wants to talk about follow-up questions on any of the things we discussed today, or you have a particular challenge on a current project or a question you've always been wanting to have answered. We can do our best.
Katie, KJ Morris asked earlier, can you address retrofitting an older building, perhaps even a historic log structure with heat pump?
So ideally, in any kind of retrofit, we would always want to understand, well, what are the opportunities to improve the building envelope and tackle that first. You know, in a historic log structure, it's certainly very challenging. You'll be limited by what you can do. Presumably you want the log finish on the inside and outside, so probably aren't going to want to, you know, add a layer of insulation. I think some air tightness improvements, that's always available in terms of what's accessible and how many improvements you might need to make, or you might be able to make. And after that, I would say even in a structure, even if you're not upgrading the envelope very much, again, heat pumps are just inherently more efficient. So, you know, then it really comes down to what are space constraints? Is there existing ductwork you want to try to leverage? What sort of drop ceilings are there? If there's a crawl space, could it be turned into an insulated crawl space so that you can run ducts in there and not have to worry about, you know, heat loss associated with those? So, but yeah, it's without knowing more, and generally speaking, anything's possible. It's just understanding the bigger picture.
Okay, thank you.
Toby, would you like to unmute yourself and ask your question, since we're sort of moved to the Q&A section?
Am I muted?
No.
Okay. Yes, I just, Katie, I posted a question there to see if you've ever compared the use of point source insta-hot water systems versus the we're discussing from just a consumption perspective.
So when you say point source insta-hot, so basically an electric, it's an electric water heater, but it's like a flash water heater that's near the where you need it.
Correct. It just, you know, which in theory eliminates the storage loss from stored hot water.
Yeah. Yeah. So I think, you know, those insta-hot kinds of devices can really make sense, especially if it's a kitchen, you just want a quick little bit of hot water. Ultimately, yeah, you can find kind of energy usage reports on those, assuming it's, you know, how much you're using it, what the annual energy use would be. Aside from that, though, the typical water heater is adequately insulated now, and the savings you get from heat pump technology versus the losses you get from just having ambient loss through the tank, the heat pump benefits still by far overwhelm those standing losses. I would say, with the exception of, you know, maybe there's it's a commercial building and there's some bathroom, you know, far away from everything else that gets used you know, a couple times a day. In that case, running a long line over and trying to get efficiently produced hot water over to it, and the pump and losses in the piping and everything. And, you know, in that case, something like point of use could make a lot of sense. So it always depends. But in a typical residential situation with relatively high hot water needs, heat pump water heaters are by far going to be a more efficient way to go.
Okay. Maybe I could spin that off that same question I posted earlier. And I don't know where you stand on the use of radiant floor heat altogether, but have you experimented with using the heat pump water heaters in conjunction with in-floor hydronic heating?
Yeah, and Kara, why don't you jump to that? I can go back to that slide. But yeah, we did talk about an air-to-water approach with the Solstice heat pump. There are other air-to-water heat pumps that will work for that. But yeah, in-floor water heating, certainly great way to go. You can also do in ceiling, by the way. Then you're not blocking that heat with rugs and couches and everything. But yeah, very, very feasible and great way to go. Kara, anything else you want to kind of note on that?
Yeah, I think, Toby, you were talking specifically about using the sand-in for, that was a question earlier.
Yeah, and the fundamental question really is using these heat pump water heaters rather than boilers for floor heating.
So I know on the sand-in, you can use it for smaller areas of radiant floor heating, but you have to be very careful about how it's piped, because the efficiency of the sand-in, a lot of that comes from the stratification in the tank. And so you don't want to be mixing that tank temperature water. I guess we've done it. You do end up losing some of the efficiency of the sand-in if you tie in radiant floor heat to it.
Yeah, the trick is to make sure we're returning as cold temperatures as possible. But are you talking more in general, Toby, about just an air-to-water heat pump, whether it's the Sandin or another unit, like in this case shown here, the Solstice?
Yes, like I've at some points I've used like Radiant Tech is a brand that offers these packaged. They're hot water heater powered hydronic floor systems rather than a full boiler, they're a little bit simpler systems, less expensive systems to begin with. And so I've just wondered if you've kind of crossed that threshold using these heat pumps as your heat source for floor heat. And it's, the in-floor heat is just always such a desired thing in high-end residential construction, that one of those things that people they're just going to gravitate towards regardless of efficiency. Sometimes they just like the way it lives. And so I'm always curious about how to improve that system. If you've got a client that's going to insist on in-floor heat, it's the best way to provide it.
So if it's a larger home, I would say going with the air-to-water heat pump, and then you can pull your domestic off of that system, as opposed to going with the heat pump water heater to heat your floors.
One thing that I would add to this conversation is to confirm what Toby's saying, that there are people who insist on radiant floor heating because they love their experience with it. But I feel that it's important to note that when we are designing a whole building that is calibrated to this very, very low level of energy need, the comfort level is so much higher than any of us have really experienced. And so that cold slab, that cold floor feeling that people are used to just doesn't really exist anymore. And we can get away very easily without feeling like we need that warm floor. and a very, very tiny mechanical system does the only work that's needed.
Sure. Yeah, but I think the hardest clients are the ones, we get the clients that are very deliberate and they come from the beginning. They want to strive for these energy goals that we're talking about. The harder ones are the folks where it's more of an upsell from us.
Yeah,
We're trying
completely.
to push them in this positive direction. They're only half committed. So there's always kind of a middle ground you're trying to find.
Yep.
But yeah, Lindsay, it's a great point. And I think, you know, clients often tend to come to you and they say like, oh, I want in-floor heating or I want solar panels. And then the question is always like, well, why? You know, why do you want in-floor heating? And usually it's because they presume it to be more comfortable. They've had uncomfortable homes. And once you talk and talk, often what ends up being the case is like, it's not really in-floor heating they want. It's just, they just want to be comfortable in their home. It's not like solar panels they want. They just want to like minimize their environmental footprint. And so always asking why and getting to that underlying motivation, that underlying need is always really helpful conversation. And then, you know, in this case, Kara, I don't know if you would just want to comment a little bit. So, so again, this heat pump does have that cold weather. At a certain point, it just won't operate anymore. And so how are we integrating backup into this system in this example?
So this one, because it is high performance for the whole guest house, the walls, the ceiling, the loads are low enough that we were able to use electric elements in the buffer tank to provide the backup heat, and then using controls that will handle that staging between when the heat pump isn't providing enough heat in that tank, then it pulls on the electric element. Controls are really crucial, making sure you get the controls right to get it to operate. So you are using the heat pump to its full capacity before that electric element comes on. On a larger home, you're not going to be able to do that with electric elements in the buffer tank, so you will have to have a backup boiler.
Good afternoon.
And then, yeah, Lindsay, you were coming in before on the drop-in efficiency. In this case, the term we're going to look at is that COP that you see on the schedule here, coefficient of performance. You know, in theory, electric resistance has a COP of 1, just for reference. So this would be, you know, almost twice as good. So, but this chart that I pulled from Kira's plans here for this project this is a COP of 1.86 at -5 ambient air temperature. You know, that's pretty amazing. If you're at 17, your COP is 2.35, and it's above 3 at 47. So, you know, sure, there are going to be times where it's below 0, but for most of the year, this is operating at really high COP, and it's just significantly less energy use, environmental footprint, everything goes along with that compared to the typical design that would have an electric boiler.
I think the COP also reflects, like, if you put 1 unit of energy into the system, the COP equals how many you get out. So if for 1 unit of energy, you get 1.86 back, even at 5 degrees.
Yep.
But some of these heat pumps go up to, say, 3, 4, 5 COP.
On the sand in itself, yeah, with it has, I think its COP is like 4.5 at around 40 degrees. So it's pretty amazing. And yeah, we have done a number of combi space heating and domestic hot water systems with Sandon. You know, the neat thing about the Sandon is it has such high output, and it also produces such a high temperature hot water, 149 degrees is kind of the default, that in low load applications, it can be used for heating. But like Kara was saying with the Sandon, the efficiency is very dependent on having a cold return temperature to maintain that temperature striation in the tank. So there are, the engineering with a Sandon is a whole other kind of art and science compared to these other systems. But there's, yeah, a lot of really good applications with it. So any other last things before we close? Being 1:15 now, I'm sure everyone's hungry, like I am.
Hey, this is Alex. I just want to say that these are being recorded every week, and so I will upload these to YouTube and send out to the group. And so I just heard from a couple people who said that they had issues logging into Zoom when the meeting first started. So I will make sure we get these to you as soon as possible, hopefully tomorrow. And yeah, thanks so much for everyone joining in. And thank you to Katie and the whole crew and everyone else for making this happen. This is great.
Thanks so much to Love Shack for, yeah, really being the ones that made it happen, along with all the other stuff that's supported. But yeah, definitely would not have happened with you guys. So yeah, I can't wait for all the next ones. I'll be joining all of them as a tourist next time.
Thank you. Thanks, everybody. We'll see you next week, hopefully.